Welcome to the Space Telescope Public Lecture Series. Tonight's lecture, Webb's View of Galaxies Over Time by Nimisha Kumari of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers from the Office of Public Outreach. And as always, I want to thank the wonderful tech team, Thomas Marufu and Grant Justice, who brings you these webcasts. I also want to note that as of a couple months ago, they gave me the decision that the Space Telescope Public Lecture Series only. I know there are a bunch of you who enjoyed coming in person in Baltimore to come sit in the auditorium, but the management has decided that we are going to be online only. Our upcoming talks, I only have one scheduled at this time, but as always, no worries, I will make sure that we have a full schedule. On November 7th, we have a really special talk about making astronomy outreach accessible. All right, there's been a big push for making accessible products. Matter of fact, you're going to see one of those tonight, a sonification. And so Tim Rue and Margaret Carruthers from the Office of Public Outreach will come on next month and tell us all about that. On December 5th, we will have a wonderful speaker talking about a fascinating topic. I just don't know what it is right now, and the same is true in January. But I also don't know which date we're going to do in January, because January 2nd is right after New Year's. January 9th is during the American Astronomical Society winter meeting, and I will actually be at that meeting, and a lot of the astronomers in the building will also be at that meeting. So I may not be able to just push it back 1 week. I might have to push it back 2 weeks to January 16th. I will, however, know when it's going to be and announce it at next month, and if not, you will find it on the website, www.stsci.edu/public-lectures. This is our public lecture series website, and on the lower left you can see the link to our webcasts, our series of webcasts that goes back to about 2015 on YouTube. And then on the lower right, you can see that we have how you can sign up for email. And of course, on this website, we have a list of the upcoming lectures. And if you click on any of these lectures, it has a description of what is being talked about with the speaker. And after it has been recorded, you have links to the Space Telescope webcast, as well as the webcast on YouTube. We have an email list. So as I said, you can sign up at the website. Another way to get notices is to just subscribe to our YouTube channel, youtube.com, Hubble Space Telescope, all one word. And then you'll get new video notices and reminders of live events like this. And if you have comments or questions, you can send them to us via email. The email address is publiclecture@stsci.edu. Our social media on Facebook, X, no longer Twitter, X, YouTube, and Instagram. We have accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. I myself do tiny amounts of social media on Facebook and X. All right, now, news from the universe for October 2023. Our first story tonight, the dust shroud of Terzan 12. That sounds like a science fiction story. Well, it's not science fiction. It's actually science fact. And let me tell you what it really means. So what we're talking about here are globular clusters, okay? And this is a ground-based image of one of the largest globular clusters in our galaxy called Omega Centauri. This is from the Digitized Sky Survey, DSS. And one thing that you see is that there are so many stars in this cluster that the center of it is totally blown out. It's all white. Everything has melded together and you can't see the individual stars. Well, the Hubble Space Telescope, having much finer resolution than the ground, well, when Hubble looks at the interior part of Omega Centauri, it sees this. And you can actually make out those individual stars. This is what the high resolution of Hubble and good exposure allows you to do, to look at the individual stars in these crowded fields of these globular clusters. And these globular clusters have stars going all over the place, and it's really important for dynamicists to be able to study the motions of stars in these globular clusters. Now, Omega Centauri is just one. It's one of the largest of the globular clusters. There are about 200 globular clusters associated with the Milky Way. And here's a 3D excuse me. Here's the 3D representation of where they are in the galaxy. This is 111 of the globular clusters, and the solid purple lines are globular clusters above the plane of the Milky Way galaxy, and the dashed lines are globular clusters below the plane of the Milky Way galaxy. And what you can see is that they are located, roughly circularly around the center of our galaxy. All right, so they're in a very wide bulge around the galaxy. Now, if you put that in 2D, if you look at the galaxy in 2D on the night sky, you see the plane of the galaxy stretching across the sky. And if you plot those same globular clusters, here is their distribution. Again, they fill across the sky. Of course, you just can't see that it's roughly spherically distributed in this case. But you'll notice that some of them are way up above the galactic plane, okay? And so they're seen against a relatively dark background, and some are right down in the galactic plane, and they're seen against that bright background of the stars and that dark background of the dust. And today's globular cluster that we're going to look at, Tarzan 12, is one of those that's located in the dust clouds, okay? So this is sort of the center of our galaxy, and near the center of our galaxy you can see all the bright stars, but you can also see these dark dust lanes that are, blocking our view. And we're going to go into this small region here, all right, and zoom into that. And we can see in that dust lane, way down in this corner of this dust lane, that's where Tarzan 12 is. And Tarzan 12 is inside or behind these dust clouds, but it really looks beautiful. This is Hubble's view of Tarzan 12. Kind of cool. You see this large collection of stars, but some of them are blocked. You see all this brown gas, the dust up here, okay? That dust is blocking the light of the stars behind it. Whereas the Tarzan 12, or the part of the cluster you can see, has just got a tremendous number of stars all bunched together. So this is a gorgeous view of a globular cluster that is not, sitting out on its own, but is actually in the plane of the Milky Way galaxy and somewhat obscured. It's got a dust shroud of it from the dust in the plane of our Milky Way galaxy. Second story for tonight night, a shocking image of Herbig-Haro 211. Yes, it's just shocking. Let me explain why it's shocking. And to understand why it's shocking, let's start with a boat traveling across a lake. Well, actually, this isn't a lake. This is a fjord. And the only reason I know that is because that was in the caption on Wikimedia. All right, so you can see this boat moving across the fjord, and it's leaving behind it a wake. All right, well, this wake is generated by the bow of the ship, okay, and it's also in nautical terms called a bow wave, right? So coming off the bow, you see this wave generated. That's what leaves the wake in its trail. Now, if this boat were traveling at supersonic speeds, it would not be a wave, it would be a shock. And you can see that in airplanes that do travel at supersonic speeds, where they create a bow shock, okay? This is a really cool atmospheric phenomenon that happens just before the plane goes supersonic. Actually, when the airflow across the wing hits that supersonic, and you can get an atmospheric effect that condenses the water vapor in the clouds around it, and the atmosphere around it, and that you get this cool push here. But if you look at that same plane, or a plane like this, and you analyze it to get the actual shock, you can see how this is happening, okay? So when you're moving at supersonic speeds, faster than the speed of sound, okay, you get what's called a bow shock, right? So What's shocking about what we're going to show you? Because we are going to we're going to be looking at a bow shock in astronomy. Now, this happens for some newborn stars. And the class of newborn stars we're actually going to look at is called Herbig-Haro objects, okay? And these are newborn stars that have jets coming out of them, okay? So the newborn star is here in the center, all right? And this thing here that looks like a double-sided lightsaber, right? That's actually jets coming from the star. So this newborn star is spewing out material in these tiny little jets going off in either direction. Now, this is an image from Hubble, right? And you can see that there are these cavities on either side of where the star has formed. And the jet is relatively free to go out, and it's not encountering much material. So we have a new image from Webb that has two major differences. It's not Herbig-Haro 24, it's Herbig-Haro 211. It also has these jets. But however, it's running into other material, and we're viewing it in the infrared. So when you put those combinations together, you get a gorgeous image of Herbig-Haro 211. All right. And you can see in the center where this dark patch is, hidden by all that dust, is the newborn star. Spewing out of it is these jets, but it's running into interstellar material and it's producing these shocks. Just like the supersonic jet is running through the Earth's atmosphere and creating that shock wave. Here it's running through the interstellar material and creating these shock waves. So this is a shocking image, and it's kind of like shockingly beautiful too. So Webb's image of Herbig-Haro 211. All right. Our speaker tonight is Nimisha Kumari, and she will be talking to us about Webb's view of galaxies over time. Nimisha has a very interesting history. She got her undergraduate degree in Delhi, right? Yes, the University of Delhi in India. And then after that, she got her master's degree in France at École Polytechnique. And then she got her PhD at the University of Cambridge in the United Kingdom. So she went from India to France, to England, and then after a postdoc in Cambridge, she came here to the Space Telescope Science Institute in the United States. So she's already a world traveler in her academic career. And she's been here in her current position since 2020, where she is the lead for the JWST Science Operations Calibration program. And we're very happy to have her here tonight. She tells me that when she's not doing astronomy, she's usually playing with her dog and her cat. And she didn't name her cat, but her cat was, coincidentally named Stella, which I guess was a cosmic coincidence for her. So ladies and gentlemen, Dr. Nimisha Kumari.
Hello, everyone. Hi, everyone. So can you confirm that you can see my slides and hear me well?
Everything looks good and sounds good.
Thank you, Frank. So hello, everyone. It's a pleasure to be here for the STScI lecture series this evening. Thank you, Frank, for the introduction. I'm an ESA or astronomer at the Space Telescope Science Institute, where I am a member of James Webb Space Telescope team. James Webb Space Telescope, JWST, or Webb, is a joint mission of NASA, European Space Agency, and Canadian Space Agency. Here is an image of JWST where all of its components are fully deployed. Apart from supporting this telescope, I also spend time in understanding the cosmos via research, which is mainly driven by the questions related to galaxy formation and evolution. James Webb Space Telescope is revolutionizing this field of astronomy with new and exciting discoveries almost every day. So today I'm going to talk about the Webb's view of galaxies over cosmic time. You might know that the Space Telescope Science Institute is the Mission Operations Center for the James Webb Space Telescope and the Hubble Space Telescope. On the left is the picture of Hubble Space Telescope, also called HST or just Hubble, and is in operation for over 30 years now and has led to many discoveries. James Webb Space Telescope is often called the successor of Hubble, and its idea was conceived in 1996. However, it is much more powerful than Hubble. This is because James Webb Space Telescope is the largest telescope ever launched into space. While the primary mirror of Hubble is about 2.4 meters, the primary mirror of JWST is 6.4 meters. So it is considerably larger. As shown in this figure here, it is made up of 18 hexagonal elements or segments. The reason for having the segmented mirror is that the segments can be loaded, can be folded and be fitted into the rocket to send into space. A single mirror of this size is impractical to send into space. So that's why we thought of segmenting the mirror and fit into the rocket before sending it up. So now moving on to another interesting component of this telescope, the sun shield of JWST, which is shown here. There are 5 layers as thin as that of human hair, and they are as large as that of a tennis court. You can also get an idea of its size by the number of people standing beside the sun shield in this figure. You may be wondering, what is the purpose of the sun shield? So JWST is an infrared telescope, so it needs to be kept cool under 50 Kelvin. That is about minus 223 degrees Celsius. Otherwise, the infrared radiation from the telescope will overwhelm all the observations. So the sun shield is used to block the light and heat from the sun, the earth, and the moon. Now the instruments on JWST, which are used to take these observations. So behind the primary mirror of JWST, there is eSIM, and eSIM spells as Integrated Science Instrument Modules, which serves several purposes. But I mention it here because it holds 4 science instruments and a guide camera. These 4 instruments are MIRI. On the left, you can see, then FGS NIRIS, upper left, then NIRCam, and then NIRSpec. And all of these observe in infrared. Why infrared? Because infrared allows us to study objects emitting light from the very early universe. I will talk about this later on too. And because of the infrared capability of JWST, it is apt for studying the first stars and first galaxies. Now let's look at these instruments in a bit more detail. For each instrument here, so we have 4 panels: NIRCam, NIRIS, NIRSpec, and MIRI. And those 4 panels correspond to 4 instruments. And for each instrument, we have 3 to 4 components, which you can see the right after the names of these instruments. So these 3 to 4 components include imaging, spectroscopy, coronagraphy, and 3 of these 4 instruments operate in the near-infrared wavelength. Those are NIRCam, NIRIS, and NIRSpec. The 4th one operates in mid-infrared, and that's what gives its name mid-infrared instrument. Then after that, we can see the fields of view for each of the instruments, which are shown here as boxes relative to a nearby spiral galaxy. You might be familiar with this galaxy. Actually, this nearby spiral galaxy is called NGC 5194M51. It's a very famous galaxy with a lot of star-forming regions within it, but here we are only showing the black and white picture. And if on a colored image, those star forming regions would appear as pink blobs, and I encourage you to Google this Galaxy M51. And so these square boxes on each of these 4 panels on this Galaxy M51 represents the field of view of each of these instruments. Now, after that, we see that each of these instruments operate in the imaging mode and the spectroscopic mode. It's worth emphasizing that JWST is primarily operating in the spectroscopic mode. Spectroscopy continues to be the highest requested observing mode. It is about 73.6% of the requested time last year. So, and the remainder of the time was requested for imaging. And the most requested instrument by proposals, about which I will talk later too, is NearSpec, which is primarily spectroscopic instrument, and that is followed by MIRI, NearCam, and NEARIS. So why spectroscopy? So why is spectroscopy so important? So spectroscopy is a tool that astronomers use to better understand the physics of celestial objects. Like a prism which splits white light from the sun into its color components like a rainbow, Webb spectrographs dissect light into many wavelengths, and that's how we get the spectra of the objects under study. For example, in this figure, celestial objects such as stars, nebula, galaxies, exoplanet atmospheres, which are shown on the left, they emit light. And then this light carries information about these celestial objects. This light is split into its different wavelengths, which is then focused on Webb's instrument detectors. And that leads to the formation of a spectrum or spectra, depending on which mode you are observing your object. And then chemical elements stamp their unique properties as fingerprints on the spectrum, as you see on the right here, where we see different lines in carbon, nitrogen, oxygen, iron. So scientists study spectra and get information about temperature, density, chemical composition, and motions of the objects under study. In astronomy, we say a picture is worth 1,000 words and a spectrum is worth 1,000 pictures. That's how important spectroscopy is. So this giant telescope was finally launched in space on December 25th, 2021 on an Ariane 5 rocket from the European spaceport Kourou in French Guiana. Before launching, the mirrors as well as the sun shield of the telescope were folded to fit into the rocket, as you can see in these 2 figures on the right. And here is the image of JWST taken with a camera in the fairing of Ariane 5 launch vehicle just after the separation. And this is a very important image because we, the JWST team, did not celebrate the launch when the rocket was launched. It was when we saw this image that we actually clapped and congratulated each other of a successful launch. And after the launch of the telescope, this telescope deployed during its 30-day journey to the planned orbit, which is about 1.5 million kilometers from the Earth. So for comparison, Hubble is just 550 kilometers from the Earth. The orbit, which is 1.5 million kilometers away from the Earth, it was launched to be at L2 for several reasons. One of them is to keep it on the same side of the Sun-Earth-Moon system. As such, a single sun shield is sufficient to block the light and heat from the Sun, Earth, and Moon and keep the telescope cool. So the details of the deployment can be found in this YouTube link, and I highly encourage you to go visit this link, as each step of deployment is quite impressive, and specifically the unfolding of the mirrors and the sun shields is very impressive. Though it took only 30 days to reach L2 point, it took about 6 months to commission all of the instruments of JWST. During the 6 months of commissioning, a team of scientists and engineers, including myself, were constantly monitoring the telescope 24/7 from the Mission Operations Center at the STScI. Here is an image of the Mission Operations Center behind the glass doors, which could be accessed by only a few people. I was very fortunate to be one of them. I served in different roles during commissioning, as a test lead and quick look analyst in the near spec instrument team. My tasks were to monitor the health of the instrument, prepare observations, analyze data to ensure that the instrument behaved as expected during several steps of commissioning in order to be ready for science operations in 6 months' time. So where is Webb now? You can actually find this in real time, as I show here. In your web browser, you can type, "Where is Webb?" So you type "Where is Webb?" and then you go to the Google suggestions and you click on the first link. And here on this page, "Where is Webb?" you can find Webb in 3D solar system. We will come to that later. Here you see at different temperatures the different JWST instruments are. This link, this diagram here is showing different stages of JWST deployment, and then now when JWST is in operation. Here are more information about the science operations of JWST. And now we go a little bit further down and we have Webb in 3D solar system. So we are just seeing here, for example, the sun and Earth, and we have Mars. And I made this video yesterday, October 2nd at 7:28 p.m. We have here the launch date, December 25th. Our primary target is the universe. You can cross this box, and here you can find more information about how this video is made. So it is real time and real data. And the whole simulated video of this solar system is running in real time. There you have Voyager. And then here we have our telescope. You can zoom in and zoom out and look at different components as the telescope is moving in space. I'm waiting for the telescope to move around, and it actually is it was happening in real time when I recorded it. You can go today and do the same thing on internet. So now, for example, we are able to see the solar panels of the telescope and the sun shield, about which I had mentioned earlier in my talk. So these are again different parts of the telescope, and you can also look at the labeled spacecraft view by clicking on that link. So you have the instrument science, integrated science instrument module, OTE, primary mirror, secondary mirror, the sun shield, then the star trackers, spacecraft bus, earth pointing antenna, solar array, which I already mentioned. Then you have Jupiter here. You can see the relative position of the telescope with respect to the orbits of different planets. So Uranus, Jupiter. What else do we have? You can see how the telescope is moving around. And you can also see the orbits of different celestial bodies, which are actually these straight lines. And now we see the mirror of the segmented mirror of the telescope again. Now we have the Halley's Comet. Some of you might be familiar with it. And just a few seconds and you will see the view of the telescope again from where we started. So we have the moon again where we had started, and then we will see the Earth, and now the sun. So I hope that you enjoyed this video. You can go to the internet and see and explore the location of the telescope yourself. Now let's come to some of the science themes of Webb. So JWST was designed to probe questions on 4 main science themes, which includes observing the first stars and galaxies, then the study of the assembly of galaxies, then the formation of stars and planetary systems, and also the origin of life. So upper left image here shows the Webb's first deep field image, which shows some of the furthest galaxies known to us. The upper right image is that of Stephan's quintet, showing the merging and interacting galaxies, which falls under the science theme of galaxy assembly. Then the lower left image is that of the pillars of creation, showing glittering landscape of star birth. And then finally, a planet in our solar system, Neptune with its ring. So you might know that each year astronomers around the world submit proposals to use this telescope to observe their favorite target. And those proposals are then reviewed by a time allocation committee before approval. So here is a histogram of the number of proposals that were submitted for observing in the ongoing cycle of observation. So here you can see the number of proposals in the bottom axis, and on the vertical axis you can see all of the different science categories. Oh, sorry, on the bottom axis it's the observing hours and not the number of proposals, it's the number of observing hours. So what we see here is the most popular science category was galaxies and the intergalactic medium, which was closely followed by exoplanets and disks. The two categories marked in red boxes broadly fall under the category of observing galaxies over time and dominates all other science categories. So in the rest of the talk, I'm going to show you the Webb's view of galaxies over time. So to understand the importance of studying galaxies over time, let us have a look at this cartoon picture illustrating the evolution of the universe. So after the Big Bang around 13.8 billion years ago, the universe was like a hot soup. After about 370,000 years of the Big Bang, the protons and the electrons combined to form neutral hydrogen. That period is called the epoch of recombination. And that was followed by dark ages, when there were no stars or galaxies. The first stars formed around a few 100 million years after the Big Bang, and these first stars and galaxies then reionized the universe, which is called the epoch of reionization. So after this reionization era, modern galaxies formed and evolved, and currently we are living in the present-day universe. With the James Webb Space Telescope, we are now able to look back in time. continuously up to 13.8 billion years, 13.4 billion years into the past. I find it really amazing. As you saw earlier in the histogram of JWST proposals in different science categories, astronomers are highly driven to find and study the galaxies at different epochs in the history of the universe. And some of the important questions they wish to answer via these observations are: how was the universe reionized? Then what were the sources which reionized the universe? What were the properties of these first galaxies? How do galaxies form and evolve, and how do they die? How are chemicals distributed within the galaxies and across the universe? And then there are many more questions. So let's first look at the galaxies in the nearby universe. So because of their proximity, nearby galaxies and their constituents can be observed and studied in great details, which not only means mind-blowing pictures of the cosmos, but also a much deeper understanding. So starting from these two beautiful, very detailed pictures of the regions within our galaxy, the Milky Way, the left image shows the pillars of creation, which is a star-forming region. It was imaged using the near-infrared data taken with the NIRCam, and then the mid-infrared data taken with the MIRI. These are the two instruments on two of the four instruments on JWST. So the mid-infrared light shows the spar-like pillars, then the layer of diffuse orange dust that drape the top of the image, relaxing into a V shape. The densest region of dust are cast in deep indigo hues, obscuring our view of the activities inside the dense pillars. We may also see a myriad of stars spread throughout the scene, which primarily show up in the near-infrared, marking the contribution of the NIRCam. For example, the bright orange spheres lying outside the dusty pillars. And these pillars of creation is in the Eagle Nebula, which is a star-forming region. It is about 6,500 light years away. So really not very far. So let's go a bit further, around 11,000 light years away, where lies Cassiopeia A, which is a supernova remnant. And what is a supernova remnant? It is a structure resulting from the explosion of a star in a supernova. This image was taken with MIRI on the remnant's exterior. Orange and red emission is due to the warm dust, and that marks the ejected material from the exploded star. The bright pink filaments in the interior of this shell represent the material from the star, and they likely shine due to a mixture of heavy elements and dust emission. This region is not only very beautiful, but also quite complex, and it's kind of a mystery to the astronomers, and they are working on it to understand its complexity. Now, moving further, about 161,000 light years away, there lies a dwarf galaxy called the Large Magellanic Cloud. The image here shows the Tarantula Nebula within the Large Magellanic Cloud. It is the largest and the brightest star-forming region in the local group of galaxies. And what does local group of galaxies mean? It is the group of galaxies nearest to our Milky Way. So like the pillars of creation, the Tarantula Nebula shows stars and dust. However, what makes Tarantula Nebula different and special is that it has a similar type of chemical composition as the gigantic star-forming regions observed at a time when the universe was only a few billion years old and star formation was at its peak. That epoch in the history of the universe is also known as the cosmic noon. So what we can do is we can compare the Webb observations of Tarantula Nebula with the deep observations of distant galaxies in the cosmic web and develop a better understanding of physics in play at such later epochs. Now, here we see the near-cam imaging of Tarantula Nebula on the upper left, and then the near-spec IFU spectroscopy of a region within it. So earlier I showed you that different instruments on this telescope have different modes, and IFU spectroscopy is one of those modes. It basically allows us to take a spectrum of every pixel in an image, which allow us further to create images of various properties encoded within the features at different wavelengths in the spectra. So for example, here in the lower panel, the blue image shows atomic hydrogen mapped at 1.87 micron. So that is the wavelength of light. Then green image shows the molecular hydrogen, which is mapped at 2.12 micron. And then red image shows dust at 3.3 micron. So the image here, on the left, which shows the atomic hydrogen, this image indicates that most of the atomic hydrogen is in the star, but not in the surrounding region. The surrounding region, on the other hand, is instead filled with molecular hydrogen and dust. Thus, with Webb, we are able to get a very detailed distribution of the constituents within this nebula. Now let's go much further. Going further at 32 million light years away, we have the Phantom Galaxy. It is a grand design spiral galaxy, and what that means, it means that it has prominent and well-defined spiral arms, unlike the patchy and ragged structure seen in some other spiral galaxies. So here we have a very beautiful sharp image from Webb. So, and this image has revealed delicate filaments of gas and dust in the grandiose spiral arms of this phantom galaxy. And these spiral arms then wind outwards from the center of the galaxy. A lack of gas in the nuclear region is found, and that provides us an obscured view, an unobscured view of the nuclear star cluster at the galaxy center. And why unobscured view of the nuclear star cluster? Because the image is taken in Miri. So everything which is within, which was obscured with the dust, with Miri, we can see the unobscured view of the galaxy. And this image was a part of a larger effort, which is led by the FANGS collaboration, and that the effort is to observe 19 nearby star-forming galaxies. Now, Stephan's quintet. I already showed you an image of Stephan's quintet earlier while talking about the science themes of JWST. It is a visual grouping of 5 galaxies and is best known for being prominently featured in the holiday classic film It's a Wonderful Life. However, in this grouping of 5 galaxies, there is one galaxy which resides 40 million light years away from us, and there are 4 other galaxies which are 200 million light years away. So this galaxy which is shown in blue, that is the one which is close, and the other 4 are the furthest ones. However, this distance is still very close. And because of its proximity, Stephan's quintet is a fantastic laboratory for studying how interacting galaxies trigger star formation in each other, and how the gas in these galaxies is being disturbed, which leads to star formation again. Now, Stephan's quintet again. Webb also observed Stephan's quintet with Miri, both in the imaging mode and the integral field spectroscopy mode. The integral field spectroscopy mode, or the IFU mode, focused on the topmost galaxy, It is called NGC 7319. It harbors an active galactic nucleus, which is a super massive black hole, 24 million times the mass of the sun. The MIRI instrument saw the gas near the supermassive black hole at a level of detail never seen before, and it was able to determine its chemical composition. So on the right, we have two panels, and each panel shows a spectrum. The top spectrum is from the black hole's outflow, and it is showing a region filled with hot ionized gas, including iron, argon, neon, sulfur, and oxygen, as denoted by the peaks at given wavelengths. The presence of multiple emission lines from the same element with different degrees of ionization is very valuable for understanding the properties and the origins of the outflowing gas. And now in the bottom panel, we have a spectrum revealing the supermassive black hole, which has a reservoir of colder dense gas with large quantities of molecular hydrogen and silicate dust that absorb the light from the central regions of the galaxy. So if you are at the STScI, I encourage you to explore this group of galaxies on the tactile display table, whose picture is shown on the upper right. And let's now listen to the data of Stephan's quintet, which was collected by several observatories and has been translated into a rich layered audio experience. I will pause now, and Frank, could you please play the video for us?
Sorry, 1 second. I forgot to hit the magic button.
No worries.
There we go. Now it should work. Uh-oh. I just crashed. So go back to your screen share for some reason.
Yeah, no worries.
Go for it.
Yeah. Can you see and hear me properly?
Yep, everything looks good.
Great. So it's unfortunate that we could not hear it, but the video and the audio is available online, so you can easily Google exploring Stephan's quintet with multiple senses, and this video will pop up. These tools consisting of tactile display table and data sonification are, I think that they're very useful to the community in general, and especially to the visually challenged people who can listen, enjoy, and then further learn by reading to understand what exactly is being heard. I would also like to mention that I am very fortunate to work with a visually challenged but very talented astronomer based in Spain, and he continues to inspire me all the time. So let's go to the next galaxy. So in the Stephan's quintet, the furthest galaxies we saw were 290 million light years away. Now, Cartwheel Galaxy, we are going even further. This galaxy is about 500 million light years away. This galaxy is thought to be formed as a result of a collision between a large spiral galaxy and another smaller galaxy. And it has not only retained a lot of its spiral character, but it has also experienced massive changes throughout its structure as a result of this collision. So this image here is a composite image created by combining the NIRCam and MIRI data. In NIRCam imaging, the galaxy displays many individual blue dots, which are individual stars or pockets of star formation, and also a smooth distribution of the older stellar population and dense dust can be seen in its core. When we compare them to the clumpy shapes, which is outside, and those clumpy shapes are associated with the younger star populations. And then again, MIRI imaging mainly allows us to probe the dust content of galaxies, which is the same for Cartwheel Galaxy as well. Now, Cartwheel Galaxy is at a distance of 500 million light years. In cosmic terms, this is still fairly close compared to more distant galaxies, which are about billions of light years away from us. So at extreme distances, astronomers use the redshift reference to account for the fact that as the universe expands, the wavelengths of light are stretched and shifted to redder wavelengths, which are longer. So shorter wavelengths, for example, ultraviolet and X-ray, are toward the bluer end of the electromagnetic spectrum. So extreme galaxies in the early universe are referenced by how much the light emitted there has been shifted as it traveled through space to be detected by a telescope. We now look at some of the distant galaxies, but we won't mention their distance in terms of light years anymore, but we are going to mention them in terms of redshifts. So higher the redshift, farther is the object. And the way I have designed my slides, I will be going from lower redshift to the higher redshift. So closer objects to the higher, to the distant objects. But before that, I'm going to show you how you can explore the distant galaxies with JWST dataset. So we can access these dataset on this website created by the JWST collaboration, which is based in Europe, US, and Canada, and they have been using JWST. Mainly it's NIRCam and NIRSpec instruments. And let's see how you can explore it. So first you go into a web browser, you type JWST, you go on the first Google suggestion, the information comes up. Here you have JWST, JWST, which stands for Advanced Deep Extragalactic Survey. You can find more information in about, then there are contents for public and for scientists. Let's go into the viewer, interactive viewer. You click on the open viewer thing, and here is the mosaic of all the data taken with JWST, not with JWST, JWST in for the JWST survey. You can find more information about JWST survey by clicking on I, which stands for information. Then you can set the image settings. Then you can zoom in and zoom out by clicking on plus and minus. And then on the stacks on the right, you can see which are the different bands which have been used to create these images. 3 bands for 3 different colors, RGB. And then you can click on different options available to look at different images. For example, this one was 0.9 micron, then 1.5 micron. Let's go back to the original RGB image, and then the lower stack. Here you have NIRCam catalog, then you have NIRSpec spectra. Let's click on that. And then you have so many galaxies which have popped up. Let's zoom in here. And now you have so many yellow circles, and we click on one of them. And what we find here is a galaxy at redshift of 2.868. It was after the cosmic noon I mentioned earlier. Then there is this another galaxy about a redshift of 4.8. Then a galaxy 6.2, which is in the epoch of reionization. Then again 4.5, then 5.8. And then there is this galaxy much closer at redshift of 2. Here we could not determine the redshift of the galaxy. And here again redshift 5. 7, this is the furthest so far in all of the images we have seen now. Then another closer one. You can see the very bright emission lines here. And those are the emission lines which contain information about the galaxies, like the chemical composition and several other physical properties. So you can explore all of these things yourself. Now, let's go into looking at some pretty pictures. So here we have the Webb's infrared image of the galaxy cluster El Gordo. And El Gordo means the fat one in Spanish. And this galaxy cluster is revealing hundreds of galaxies, some which were never seen before at this level of detail. So El Gordo acts as a gravitational lens. And so what it means is that it it distorts and magnifies the light from the distant background galaxies. And two of the most prominent features in this image include the thin one, which is called El Flaca, highlighted in box A, and then we have the fish hook, a red swoosh, highlighted in box B. Both of them are lensed background galaxies, and the insets at the right show the zoomed in view of both of these objects. So this El Gordo cluster is at around a redshift of 0.87. Now we go further, redshift of 3. With near-spec IFU spectroscopy, Webb discovered a cluster of massive galaxies in the process of forming around an extremely red quasar. So what is a quasar? A quasar is a special type of active galactic nucleus, which is a compact region within a supermassive black hole at the center of a galaxy. So gas falling into a supermassive black hole makes the quasar bright enough to outshine all of the galaxy stars. This quasar here is one of the most powerful known galactic nuclei that's been seen at such an extreme distance. The near-spec data shown here, they also showed 3 galactic companions to this quasar, and they show how they are connected. So this result will expand our understanding of how galaxy clusters in the early universe came together and formed the cosmic web we see today. And remember these cosmic knots and cosmic web, because we will come back to them later. So this image from NASA's James Webb Space Telescope is of a massive galaxy cluster called WHL 0137-08. Too difficult to remember for me. It contains but I did remember. It contains the most strongly magnified galaxy known in the universe's first billion years. That is called the Sunrise Arc. It is you can see that in a rectangular box, and within that galaxy is a very distant star. Until a few months ago, it was the most distant star ever detected. This star is nicknamed Erandel, and it was first discovered by the Hubble Space Telescope. The follow-up observations using Webb's NIRCam instrument reveals that the star is a very massive B-type star. So there are different types of star, O, B, A, F, G, K, M, and this is a B-type star, and it is more than twice as hot as our sun and about 1 million times more luminous. The interesting thing is that based on the colors of Earendel, astronomers now think that they see hints of a cooler, redder companion star, which is quite interesting at such a redshift. And we think that this could be a step forward to the eventual detection of one of the very first generation of stars composed only of the raw ingredients of the universe created in the Big Bang, so hydrogen and helium. So this observation was at a redshift of 6. We are in the epoch of reionization. And now let's go even further, redshift 7, that is about first billion years of the Big Bang. Here is a very cool result where Webb observed the chemical signature of carbon-rich dust grains at this redshift, like first billion years of the Big Bang. So these kind of observational signatures have been observed in the much more recent universe and is attributed to complex carbon-based molecules, which are also called the polycyclic aromatic hydrocarbons. It is not thought likely, however, that PAHs or polycyclic aromatic hydrocarbons would have developed within the first billion years of cosmic time. So therefore, this observation suggests the exciting possibility that Webb may have observed a different species of carbon-based molecule, possibly minuscule graphite or diamond-like grains produced by the earliest stars or supernova. This observation suggests exciting avenues of investigation into both the production of cosmic dust and the earliest stellar populations in our universe, and it is really amazing. Now, I talked about cosmic knots earlier and cosmic web earlier, so now we go into the cosmic web strands. So our universe is a web-like structure of galaxies called the cosmic web. And galaxies are strung along filaments in this vast web, which also contains enormous voids. This image is that of a deep galaxy field from Webb's NIRCam instrument, showing an arrangement of 10 distant galaxies marked by 8 white circles here, if you could see, in a diagonal thread-like line, which represents an early strand of cosmic web, which existed around 830 million years after the Big Bang. And this structure is about 3 million light-year long structure and is anchored by a luminous quasar. And what is a luminous quasar? I mentioned briefly, a luminous quasar is a galaxy with an active supermassive black hole at its core. And this early thread of the cosmic web is believed to eventually evolve into a massive cluster of galaxies. So that is very interesting. Now, this image shows 7 galaxies which have been confirmed to be at a redshift of 7.9. So we are going even further. This redshift correlates to 650 million years after the Big Bang. This is the first time that a protocluster of 7 galaxies has been observed at such an early time. It is sort of early universe prequel to huge galaxy cluster. And what does that mean? It means that it will likely grow in size and mass to resemble the Coma cluster. You can Google Coma cluster later. It is a monster of the modern universe. The prediction that the protocluster will eventually resemble the Coma cluster means that it would eventually be among the densest known galaxy collections with thousands of members. And now some more interesting results. This image here shows the discovery of the most distant supermassive black hole, which existed just over 570 million years after the Big Bang, and it weighs only 9 million solar masses. So to put this into context, the black hole at the center of our Milky Way is about 4.6 million times the mass of the Sun, and the other very distant supermassive black holes we have known about for decades, weigh more than 1 billion times the mass of the sun. So in the lower panel on this figure, we have spectrum of this object in white, which peaks at around 4.71 micron. So that's the wavelength, showing the detection of hydrogen. And Webb's data are then fitted to two models because more than one source is responsible for the shape of this data. The broad model is at the bottom, which is represented in yellow, and it fits the faster gas swirling in the black hole's active accretion disk. And then the purple model with a high peak fits slower gas in the galaxy. And this is emission from stars that are actively forming. These initial findings suggest that the less massive black holes and galaxies might have been more common in the early universe than we had thought previously. Now, the Webb's discovery of earliest galaxies confirmed to date by spectroscopy. I mentioned spectroscopy because it is more reliable to confirm the distances of galaxy with spectroscopy than imaging. So on the left is again a near-cam image. In the middle panel are the zoomed in view of 4 distant galaxies known, and then on the right are their spectra taken with the near-spec instrument. The light from these galaxies have taken 13.4 billion years to reach us, as these galaxies date back to less than 400 million years after the Big Bang, when the universe was only 2% of its current age. So to be able to probe a galaxy so far from us is really mind-blowing. An interesting observation in these spectra is that there are no metal lines. You might remember that I talked about several metal lines like iron, oxygen, carbon, but here there are no metal lines, which is likely because the universe was not as chemically evolved to produce the metals which are abundant now in the nearby universe. And now here is the near-cam image of a slice of the sky known as extended Gauss strip. And it is showing several zoom-ins highlighting the candidate of the furthest galaxy. And the furthest galaxy, it is estimated to be at a redshift of 14 now, which means around 290 million years away. So if it is confirmed by spectroscopy, then it is the furthest. So this is my last slide. I hope I convinced you that Webb is revolutionizing our understanding of the universe, and I would like to thank everyone, so many members from NASA, ESA, CSA, STScI, who have been working tirelessly, and they are the ones who have produced all of these materials. So thanks to all of them, and thanks to you for listening. I will stop sharing my slides now.
All right. Well, thank you very much, Nimisha. That was quite the breadth of the universe that you covered, going from, a few objects inside our own Milky Way galaxy, all out to the most distant star ever was observed and the most distant galaxies so far ever observed. I just got a fact that, this is only a year and a half in. So we're really expecting none of these records to stand, right?
Yeah, so for example, the galaxy which I showed you, it's called Macy's Galaxies, and it is thought to be at redshift of 14, and this was done, I think, a couple of months ago in August. And before that, when I showed you 4 different galaxies from redshift of 10 to 13, that was done in December. So within 6 months' time, the record has changed. So who knows, in a couple of months, we will be probing even further universe. Yes, of course.
And the Arendelle, the formerly most distant star, I haven't heard about the new most distant star.
Yeah, so the new most distant one is found in the El Gaudor cluster. So Arundel is about 5 billion years, and 5 billion years, yes. And the other one in the El Gordo field of view, we have this another star which is Quirrell, and it is a red star, and that is 4 billion years after the Big Bang. So that is, and that is the first time we are observing a red star like that. So yeah, at such a distance, yes.
And so, and just to clarify for the audience, that these are found in these gravitational lensing clusters, simply because they stretch the light so you can see the individual stars, and they magnify it by so much, right?
Right, exactly. I mean, we couldn't have done this. Who knows? In the future, we could probably, but these observations of stars have only become possible because of the gravitational lensing, and it's really amazing. Yes, of course.
Okay, fantastic. All right, well, we've had a bunch of people online watching this on YouTube, and Grant Justice has been following the chat on YouTube. And I always bring him in at this time to pull up any questions that we have from our online audience. Welcome, Grant.
Hello. Yeah, absolutely. First off, is Arundel a reference to Lord of the Rings? Because I love astronomers.
Yeah, exactly. I mean, yes. So yeah, the reference is there, and I think you would know, and the people in the audience would know more about Randall in terms of Lord of the Rings than me. I know there are several.
I actually have to disagree with that, because the naming of it is because it's the morning star. It's seen in the morning of the universe.
Yeah, it does mean morning.
Okay. Yes.
Yeah, morning
now
star,
it happens to also be in Lord of the Rings, which means morning star. But I heard from in one of our news meetings that no, it's not taken from Lord of the Rings. It's taken from its meaning to be morning star.
Oh, okay.
Sorry, Tolkien fans. You can still claim it, because it's still kind of fun.
So there was something that you said that the audience and I wanted to expound on a little bit. I don't think I've ever heard someone describe a celestial object in terms of size using light years. Is that because you're looking at it through gravitational lensing, or could you expound on that a little more?
Size using light years? Yeah, you can, because light years is the measure of the distance, right?
Yeah, absolutely. It was just
So the distance which is covered in a year by light would be light year.
Okay, so which observation were we? Was this a gravitational lensing observation that we're getting down to light year scales?
No, actually,
Grant, I think I'm not sure which observation who's referring to.
It was about a Tarantula Nebula where yes. I showed it's a Tarantula Nebula in the Large Magellanic Cloud, which is 161,000 light years away. And on that image, I had a scale which was 50 light years across. But using that scale, you could measure the size of the object too. So yes. Yeah.
Okay. I mean, and that's just because the LMC is relatively close in the universe.
Exactly. So. Yes.
Relatively. There's always something, at least one thing per presentation that makes me remember the incredible scale of everything going on that we're talking about. All right. So one of the other things that you mentioned a little bit, and we've heard bits and pieces here, but when you're talking about the difference in your individual observations, you discussed using multiple telescope observations, or multiple, what would you call it?
Observing modes.
Observing modes, yeah. What is it that each one obviously allows you a little bit different, but could you give an example of something that you've done recently where you used, for instance, like MIRI and JWST and, for instance, like a ground-based observatory, all leading you to a singular or like conclusion?
So, for example, I showed some nearby galaxies, and then there was this phantom galaxy. Phantom galaxy has been studied a lot, and it, for example, I myself So one of the projects I did a few years ago, one of the first projects was with including this galaxy, phantom galaxy NGC 0628, and then that galaxy was taken with a small telescope relatively. It is the KPNO CTIO telescope, which imaged in optical. Then after that, this galaxy was also observed with the mid-infrared instrument, which was Spitzer, then also with Herschel, another far infrared instrument, then with the VLA, very large array, with which observed the atomic gas content of the galaxy. Then the molecular gas of the gas content of the galaxy was observed using IRAM, the Plateau du Biot, which is in Plateau du Biot, which is in Europe. So so all of these observations were taken before, and then after that, all of these based on the results from all of these different ground-based instruments and space-based instruments like Spitzer and telescopes like Spitzer and Herschel, we this team called FANGS Collaboration, they have put up a sample of 19 spiral galaxies, which are going to be observed with or like some of them are already observed with with JWST, and there it is going to be done with MIRI, mid-infrared. So the galaxy which I showed was with the Phantom. I know that there are a few more galaxies in the sample which have been observed with MUSE, and they are in the same sample, and these are all star-forming galaxies. So that is an example of the spiral galaxies. Now there are many more other objects which I have shown, which were actually based on the previous observations with other telescopes. So yes, all of these existing instruments are forming base or guiding us to make observations with JWST and make best use of it. Did I answer your question? Was that your question?
Yeah, absolutely. It seems more like it's a synthesis of multiple observations, multiple types of platforms, because you're trying to get a breadth of what it is, and what it returns and what it doesn't kind of gives you an inkling as to what further you want to research.
Exactly. Yeah. And also we have been using this a lot, like different instruments on JWST. We are using them in such a way that they complement each other. For example, we take images with NIRCam, then we say, okay, from in NIRCam we see these objects and these are very interesting. So we are going to do follow-up spectroscopy with NIRSpec. And in NIRSpec spectra, when they are taken, they can be used for several purposes. One of them is confirm the distances of very high redshift galaxies, and then after that to study the chemical composition. And those chemical composition or properties, they are going to tell us more about the distant universe. Then, so these instruments can be studied, can be used in a complementary way as well. So it's a really great facility where each instrument is complementing each other.
So I had another question that I wanted to delve a little bit into regarding the JADE survey. Okay, which is a deep extragalactic survey. And as I said earlier, this is only 1 year's worth of observing time and such. The efficiency of the detectors on JWST is like 10-15% better than we actually expected it to be. And we're getting so much depth in the images on this. How many, like, if we put in the same sort of observing hours that we put in for Hubble on the ultra deep field and such, we really expect to see a tremendous more of these things. Are we going to have a son of JADES or a continuation of JADES in working on this?
So JADES, yes. So for example, JADES is not even complete yet. So observations are still. So what I showed you was the deep field observations, which are available now for public. There would be some data release happening again, where we will where you can see more data which have been taken, and then there are more data being taken even as part of JADES. And after that, there is cycle 2 program, which whose observations which will also be taken, which are even deeper for these objects, and those will be like near cam and near spectroscopy. And the interesting thing is that, which I did not mention because it's a little bit, it's very complex. Like talking about spectroscopy is complex, and near spec is so wonderful, and it has so many different modes. For example, the micro MSA, the MOS mode, the multi-object spectroscopy mode, about which I did not talk. And since you have asked me the question about JADES, JADES actually capitalizes on the MOS mode, where there are so many shutters which are open, and then in each shutter, well, not in each shutter, but in each slit, which is made up of a few shutters, there is an object, and you can observe multiple objects at the same time and take their spectra. And those will be taken to like the same people who have led JADES are also leading this cycle 2 program, and hopefully we will have great data and we will know much more about the universe.
Right. Yeah. And to be able to take advantage of that programmable microshutter array is an amazing capability with this new telescope. Exactly. All right, Grant, we're getting to 9:20. Do we have another question on the line that we want to delve into?
Yeah. Here we go. Hold on. Let's see. Where have Earth-like planets inserted themselves into your studies? Have you had any observations on them?
Oh, me?
Yes, you particularly. We want you to have made the discovery.
Okay, so not me, but I help people in taking observations of planets. Like there have been observations taken for the planets in our solar system and planets outside the solar system, which are called exoplanets. And yes, people are very enthusiastic, as I showed you on the histogram, where there was this big bar about galaxies and intergalactic medium, and then there was this another bar which was dedicated to exoplanets. So yes, people are very excited about studying exoplanets and the signatures of life, which are actually you can also, I would like to emphasize, because I'm a spectroscopist, and JWST is primarily a spectroscopic instrument. So all of these signatures, the chemical composition of the atmospheres of these planets, they can be studied in the spectra of these objects. So yes, people are doing it. Not me, though.
Well, that's the beautiful thing about science. Everyone's a part.
Yes. Well, we haven't quite gotten to any of the major breakthrough discoveries in terms of extrasolar planets, but we know they're coming as we're working through this, because Webb has found a ton of new stuff in everything we're looking at as we look at these things. All right. This was a wonderful exploration. Another take a look at getting out to, really just, I have a hard time believing that we've actually got something at redshift 14. Okay. Let me just say that. Okay. Having done my PhD in cosmology, I'm just like, no. We're not seeing redshift 14. I'm gonna need to really look at those papers in detail. We're getting out beyond where we had expected, and we will continue to do so. So thank you, Nimisha.
Thanks to you.
November 7th, we will continue that discussion of accessible astronomy that you showed with Stefan's quintet. Tim Rue and Margaret Carruthers. Everyone, please come back and join us. Until then, thank you for watching.
Bye-bye.